This is a lesson in university physics, calculus-based physics, on solving RC circuit problems where you have a resistor and a capacitor, and this is direct current DC circuits. In a previous video, I had laid out sort of the theory and talked about how capacitors act in RC circuits as a function of time. We have charging or discharging circuits, and the capacitor acts like different circuit elements at different points in time, whether it's charging or discharging. So we're going to use those properties in order to solve some problems. I hadn't solved any problems in the previous video, so this is an opportunity to pick up how to solve some of those problems with the concepts that was covered there. The first problem I have is just a simple charging circuit. We have a resistor, an uncharged capacitor, and a battery are connected in series. So I'm going to draw this out. I like to put my battery on the left, and then we're going to put a resistor in here, and then a capacitor, and then connect them all together. So there's a C, an R, and a V. This is my first drawing. I'm going to draw a few more. Remember what I said about the capacitor acting like different things at different times? I'm going to draw that as appropriate for this problem. Part A asks, what is the initial current? At t equals 0, what is I of 0? And I know you might want to try to find an equation, that's time dependent where you plug in t equals 0 to do this. But what I'm going to do is I'm going to redraw the circuit here, and I'm going to ask myself, what's the capacitor doing at t equals 0? At t equals 0, if I go back to that slide and I look at that slide, at t equals 0, when I'm charging, that capacitor is acting like a wire because it's easily accepting charge. It's an uncharged capacitor. That capacitor is easily accepting charge, so it's going to act like a wire. And when I look at this circuit, I'm going to have the battery, the resistor, and then the capacitor acting like a wire. Like, it's still there, but when I think about how it's effectively acting in the circuit, it's just a wire. So when I look at this circuit, I just have a battery and a resistor. I can do a loop. The voltage over the battery has to be equal to the voltage over the resistor. The voltage of this capacitor equals 0 at this point in time. It has no charge, right? Because Q equals 0, and it's acting like a wire. So the initial current, I, has to equal the voltage over the battery divided by the resistor. The voltage over the battery is 10. The resistor is 300. And we're going to get, 33.3 repeating milliamps. So that will be the initial current in the circuit. I don't have to plug 0 into any equation. So if you're looking at t equals 0 or t equals infinity, you don't use the exponential equation. Only when we're in between those two times do you use that exponential equation. Part B says, what is the time constant? Okay, I like this. This is actually a plug and chug. I'm just going to take R and multiply by C. R is 300, C is 1.5 times 10 to the negative 6th, and my time constant is actually going to be, 450 microseconds. Okay, so that's the amount of time it takes to charge to 63% of the total charge. Okay, what is the current after one time constant? The current after one time constant. So we're going to say T equals tau, right? T equals tau. The current after one time constant, well, I'm going to remember that will be the time derivative of the charge, Q of t. And so that will equal the time derivative of this equation. Q max 1 minus e to the negative t divided by tau. Okay, well, you know how to take the derivative of that. Hopefully at this point in time in your calculus adventures, you know how to take the derivative of that. I of tau is going to be equal, I of t, I'm just going to say I of t in general, is going to be Q max. Going to keep the Q max out front. The derivative of this term is going to be negative e to the negative t over tau times, I have to take the derivative of the exponent, 1 negative 1 over tau times negative e to the negative t over tau. I'm just keeping track of all those negatives. You can see this negative cancels out that negative when I multiply them together. And what I'm going to get, I of t equals q max over tau e to the negative t over tau. If I want to plug tau into that equation, I get e to the first power. So I'm going to have q max over tau e to the first power. Sorry, negative first power. There's a negative in there, right? So q max, do I know q max? Q max must be, what is Q max? After a long time, when that capacitor is charged up, what it's done is the current will go to 0. So Q max will equal C times the voltage across that capacitor, which is going to be the voltage from the battery. Okay, so I'm going to take CVB over tau times 1 over E. E to the negative first power is 1 over E. So let's see, the capacitance is 1.5 times 10 to the negative 6th. The voltage is 10. The tau is R. Oh, I already found it. 450 times 10 to the negative 6, that's tau. And then I have E on the bottom. And when you run those numbers through your calculator, this cancels with this, and then we divide by E, and it's going to be a little bit of a smaller number. I get 12.26 milliamps. That will be the current after one time constant. Okay. When you're in between 0 time and infinity time, you have to use the equation and plug in the time in order to calculate a value. The last question here, what is the voltage on the capacitor after one time constant? I maybe would do it this way. The voltage on the capacitor will equal the charge on the capacitor at that time divided by C. So I'm going to have Q max times 1 minus e to the negative t divided by tau. Remember, that's the Q term, right? That's Q, the time-dependent equation of Q. And then I'll divide by C. So the voltage on the capacitor is going to equal Q max divided by C. Q max divided by C is just the voltage on the battery. 1 minus e to the negative t over tau. So what's going on basically is the capacitor is just accumulating voltage from the battery at an exponential rate, and it'll increase really fast, and then it'll cap out at the voltage of the battery. Okay, so if I want one time constant, I'm going to have the voltage of the battery 1 minus e to the negative first power, and you can plug that in. 1 minus e to the negative first power. When I plug that in, voltage of the battery, I get 10 times 1 minus e to the negative first power. E is just a number, and when you run this through your calculator, the voltage of one time constant is going to equal 6.32121 volts. Okay, so this problem isn't too bad. I like that it focuses on just one time constant. What's the voltage, what's the current, etc. at one time constant. So you're working with the time constant. Other problems, like the next one I picked out, will have you looking at current at different other times in the circuit. This is also a charging circuit. It's a little bit more complicated. We actually have 3 resistors going on. I chose this one because I see students struggle a little bit with this one, so I wanted to cover it, and then you can have some an example to go off of when you're working on a problem like this. It says in the circuit below, the switch is open. Okay, so we can see the switch is open. If the switch is open, there's no current going through this middle branch. There's only current going through this outside branch. I'm going to keep note of that. The capacitor is uncharged. Clearly, if the switch is open, the capacitor isn't going to be able to accumulate charge. And the current through the battery is 0.5 amps. So we don't know the voltage on the battery, but we know the current in this circuit to begin with. I'm going to take a second and find that voltage on the battery. All right, so if I have T, this is going to be before the switch is closed. T is less than 0, right? Before the switch is closed. The circuit's going to look like this. I have a battery here. I have a resistor here. I have a resistor over here. And this branch in the center basically doesn't exist because the switch is open, right? So when I look at this circuit, I have two resistors in series with that battery, and I know the current in it, I, right? So the voltage of the battery has to equal I from the battery, R equivalent. So I from the battery is 0.5. The equivalent resistance, you may be able to do this quickly in your head. They're in series. They're just going to add, which is 15. And so I know the voltage from the battery is half of 15, which is 7.5 volts. That's not information they were given in there, but with that amperage, I can find the voltage over the battery. I'm going to need that voltage over the battery because it's going to be what's charging this capacitor in here. So what is the current through the battery immediately after the switch is closed? Okay, so immediately after the switch is closed, if I go back to the slide, that summary slide, immediately after the switch is closed, the capacitor is going to act like a wire. Okay, so I'm going to redraw this circuit again to the relevant circuit that's happening at that point in time. So at t equals 0, I'm going to have this circuit. I still have a battery. I still have a resistor in that circuit, in that branch. The capacitor acts like a wire. There's a resistor here, and there's still a resistor here. So I think what students may slip up and do and say, the battery was 0.5 before, it's still 0.5. But what you can see is that when that capacitor, when that branch is activated, that capacitor is acting like a wire. And overall, this parallel, these two parallel resistors, it's going to offer another path for the current to flow. And that current will actually increase through the battery. Okay. I can find an R equivalent here. R equivalent, this is a 10 and a 10 in parallel in series with a 5. So I'm going to take 5 plus 1 over 10 plus 1 over 10 to the negative first power. And the equivalent resistance in this situation is going to be, what, 10 ohms? This will be 5 plus 5 is 10 ohms. So if I want to find that current through the battery, I'm going to take the voltage over the battery and divide by R equivalent. The voltage over the battery, we already calculated, 7.5. R equivalent is 10 ohms. And at t equals 0, right when I close that switch and the battery's that capacitor is easily accepting charge, that current will increase from the battery to 0.75 amps. Okay. So watch out for that. Redraw your circuit. Again, that capacitor is acting like a wire. It's acting like a different circuit than what we started out with. So draw your circuit, what it's doing, the active elements at different points in time. It says, what is the charge on the capacitor a long time after the switch is closed? Okay, so let's go back to our chart and see after a long time, after the switch is closed, that capacitor was charging, but after a long time, it doesn't accept any more charge. The current through that is going to be a break, and it'll be maximally charged. So when I draw this circuit again, is going to be like we started out with. At t equals infinity, we're still going to have the battery. The capacitor acts like a brake, and there's still a resistor over in this branch. I'm not even going to draw that other resistor because that is a brake, right? There's a brake, there's a resistor here, but this whole branch is a brake as if it's not even there. So I'm not even going to draw it in there. So this circuit looks like a 5 and a 10 with your battery. It says, what is the charge on the capacitor a long time after the switch is closed? So a long time after the switch is closed, this is what our circuit looks like. We're going to have charge on that capacitor. It's going to be a maximum charge. And so if we want that maximum charge, we're going to take the capacitance and multiply by the voltage over that capacitor. This is another point. I think this is where students get stuck on this problem. They don't know what to put in for the voltage of the capacitor, and people just kind of knee jerk and they'll say, oh, the voltage of the battery, easier problems, I just use the voltage of the battery. But when I look at this problem, and I'm looking at, there's no current through that resistor. When I'm looking at the voltage over that capacitor, I have to do a Kirchhoff's loop here. And when you're looking at this loop, right, we have the voltage over the battery. I'm going to have a voltage drop over that capacitor, and then I'm also going to have a voltage drop over that resistor. Students forget that that resistor is eating up some of the voltage from the battery when you look at that loop. So the voltage on that capacitor has to equal the voltage over the battery minus that IR. Okay, so let's plug in what we know. The voltage over the battery is 7.5. The current we already know, right? These two circuits are the same. Do you all see that? So the current has to be through that battery branch, through that resistor, it has to be 0.5, and that resistor is 5. So I get 7.5 minus half of 5, which is 2.5, and the voltage over the capacitor equals 5 volts. It's not getting all of the battery voltage. It's only getting some of the battery voltage. So I can use that number. Now I can calculate my Q max. The capacitor is 5 microfarads. I can see that on the picture there. They didn't type it out, but I can see it on the picture. 5 micros, and then the voltage across the capacitor is 5. So when I calculate Q max, I'm going to get 25 microcoulombs. Okay. So kind of cute problem, and again, I know students have a hard time with this problem because they forget about this term right here, that resistor is eating. Also, when I do this loop, it's consuming voltage from the battery. That the capacitor does not get all of the battery voltage, it only gets a portion of that battery voltage. Okay. All right, last problem I picked out here actually has you plugging in time into those exponential equations that we looked at, and this is a discharging capacitor. Okay, for the circuit shown, the switch is initially moved to position A, and then the capacitor is charged up until it's fully charged. At time equals 0, the switch is flipped to position B, so it gets flipped over there. Okay, then the battery is not attached anymore, and it's just that capacitor and the resistor. So at t equals 0, we just have a capacitor and a resistor. So I'm going to draw that in here. And so we're going to have a discharging circuit, that capacitor. Let me ask you, you can think in your head real quick. Which direction is the current flowing in this circuit? Is it flowing clockwise or is it flowing counterclockwise? I'll give you a second to think about it. You'll want to think about which plate is the positive plate of the capacitor. And to think about that, we'd have to think about, well, what was the positive plate with the battery? The battery's plate, positive plate, was on the bottom. For whatever reason, they drew it here. So it pushed positive charges here, All right, so this will be the positive plate and that'll be the negative plate of the capacitor. When we detach the capacitor from the battery, charge will flow from positive to negative, conventional current. So it will flow clockwise in this circuit. Okay. It says how much charge is stored on the capacitor at 0.8 seconds. All right. So if we want to find Q of T, we'll have to equal Q naught e to the negative T divided by tau. Okay, and then we'll be looking at when T equals 0.80 seconds. Q naught, let's solve for Q naught over here. It had to equal CV from the battery. When it was hooked up to the battery, notice that was the only thing that the resistor wasn't even in here. If I close that switch, that resistor couldn't even be attached. So the capacitor was getting all of the voltage from the battery. So the capacitor is 4.6 times 10 to the negative third, right, millis. And then the voltage over the battery is 27. So you can solve for that value. Did I solve for that value? Q naught. I did not solve for that value. I don't see that anywhere. Q naught. Oh, I guess I have it down here. Oh, what a cute number. 1242 microcoulombs. Millicoulombs, sorry. Millicoulombs. That's the Q naught. So I'm going to put that in here. 1242 e to the negative. T is 0.8, and then I'm going to have to divide by tau. I can do that over here too. RC, R is 280, C is 4.6 millis. And did I solve that for anywhere? I don't see. Oh, it's 1288 milliseconds. Okay, so I'm going to divide by 12, 1.288 seconds. Right? 1288 milliseconds is 1.88 seconds. Okay, so you just plug all that in there, right? Q of 0.8 seconds. Run that through your calculator. Just plug it in. When you do that, you should get 66.738 millicoulombs. Q of 0.8. Okay, so that's part A. Answered that real simply. How much current is running through the circuit? Current, we know, is the time derivative of the charge. I of T is d by dt of Q of T, and we can do that. We're going to get a negative Q naught over tau e to the negative T over tau. I'm going to note that this term here, isn't that what this is? So I'm going to get I of 0.8 is going to be Q of 0.8 divided by tau, interestingly. Do you all see that? Q naught e to the negative T over tau, Q naught e to the negative T over tau when I take that derivative. So I'm just going to take, yeah, I can do that, 66.738, and this is in millicoulombs, I'm going to divide by milliseconds. 1288 milliseconds. The millis are going to cancel. I get coulombs over seconds, which is definitely amps. So I get the current at 0.8 seconds is going to be 0.0518 amps. Just run that through your calculator. Okay. I know this looks intimidating. You're using this exponential equation, and then, oh, well, you kind of got to take the derivative of an exponential, which isn't terrible. It's an exponential, so it's an easy derivative. I think that solving these might be a little bit harder than what you anticipate, but really it's just plugging in numbers. Part C, I've seen students struggle with this because it says between 0 and 0.8 seconds, and we just got done doing a derivative, and I think when students see between 0 and 0.8 seconds, they want to take an integral, right? Like, it's kind of suggestive. I go from 0 to 0.8 and I'd integrate something. It says, how much energy does the resistor dissipate between that time? What I'm going to remind you is that the total energy delivered by that battery, all right, is going to be the energy of the capacitor, right? I hadn't really thought that out when I said it, but the total energy of that circuit is just whatever that capacitor had been storing. 1/2 CV squared. I could do it that way, or I could do a Q squared over 2C. That might be okay because I have a Q value. I'm going to note that the amount of energy dissipated by that capacitor, there's going to be a maximum value, and the energy dissipated by the resistor, U resistor, has to be U cap total, or max, the maximum energy stored by the capacitor when it was initially charged, and then it has to be subtracted by how much it has at 0.8 seconds. So something that looks like an integral is actually, we're going to do a little bit reverse engineering, and it asks about the energy of the resistor, but I can get that energy of the resistor by looking at that energy of the capacitor. The maximum energy is going to be Q max squared over 2C, and then I would subtract Q of 0.8 squared over 2C. So you square those two charges and subtract them and divide by 2C. So I would do Q naught is 1242 squared minus microcoulombs minus 66.738 squared. All right, I'm just factoring out the 2C's, and then I divide by 2 times 4.6 times 10 to the negative third. And that will give you that energy dissipated by the resistor. I think it's also maybe intuitive or suggestive that you might use P equals I squared R for a resistor. Remember, power dissipated by a resistor in a circuit, but it doesn't ask for power, it asks for energy. Remember, power is energy over time, and I suppose you can no, you can't even multiply by 0.8 because it's not a linear function. Okay, it's an exponential function, so that won't work either. So it's working a little bit backwards here, reverse engineering, focusing on the energy of the capacitor and then relating that to the energy of the resistor. So that should give you a leg up on that problem, and that's all of the examples I had for you to practice with today.